Right, so welcome. So this is Mike's first talk after she came here, right?
Yeah, I think I
so-
talked once before I came here.
Right. So should we talk about Babai's conjecture, right? Please.
One, I guess, of Babai's conjectures.
One of the Babai's conjecture.
Yes. So the work I'm presenting today is joint work with James Davies from Cambridge and Liana Yepremyan from Atlanta, from Emory. And it's about a conjecture of Babai's about a specific type of edge colorings. So whenever we talk about colorings in this talk, it's always about coloring the edges of a graph. And it's all about edges not being lonely, because loneliness, we want to fight that. Nobody likes to be lonely. So what does it mean for an edge to be lonely? So if I have an edge coloring of my graph, and I have a cycle in it, and all of these edges are colored somehow, then for every edge I check whether in the cycle it sees another edge of the same color. Then it's not alone, so the edge is not lonely. So in this graph, all the edges are not lonely, everybody's happy. But if I make an edge covering and I find a cycle somewhere such that one of my edges occurs along the cycle alone, then this color here will be lonely in the cycle, so there's happy. So we want to avoid that. And we say a graph is a no lonely color graph. If we can find an edge coloring such that, first of all, every vertex is incident to at most two edges of a color. So our coloring doesn't necessarily have to be proper. I can have a vertex that sees a color twice, but I'm not allowed to see it a third time. So not quite proper, but still I have a restriction on how often I see a color extent. And none of our colors is lonely. So whatever cycle in my graph I consider, whatever edge in my graph I consider, this edge sees another edge along the cycle of the same color. So this is the object we're working with, these types of colorings for edges.
So
Yes?
is every click monochromatic? So I think every click is monochromatic.
No, because I can see at most two edges of the same color, right?
So what about triangle?
A triangle can be monochromatic, but as soon as I have a K4, it cannot be monochromatic anymore.
I see.
Right, so for a triangle, this is a no lonely color graph because I can just color everything the same color. For the K4, I need more colors.
I see.
So no color is lonely means that every cycle, no cycle contains unique color, right?
Exactly.
Uh-huh.
For every cycle, yeah, exactly. No cycle contains a color that is the only color I see in the cycle.
Uh-huh.
So will you motivate the first condition? It looks
A bit. I'm gonna motivate the first condition. Also, we don't. Let me continue. I will come to it. So the conjecture that the title is about was made by Babai in 1978 and says no lonely color graphs have bounded chromatic number. So chromatic number here is proper vertex coloring, and how many colors do I need for this?
What was his motivation for that?
Same question as the one is. So the motivation for this is that one example for lonely color graphs are Cayley graphs. Every Cayley graph is a no lonely color graph. And a stronger conjecture by Babai, which was the motivation to make this one. I also have a year for this one, maybe? Yeah, same year. So this is probably also the same paper, I'm not quite sure. Is that every minimal Cayley graph sorry, minimal Cayley graphs are not only color graphs. And every minimal Cayley graph has bounded chromatic number. Or all minimal Cayley graphs have bounded chromatic number. And this is the motivation, because as every minimal Cayley graph is a not only color graph, this conjecture would imply that one. Why we disprove this one, we do not disprove this one. So this one, in the end of the talk, will still remain open. And we actually have tried to also do this one, but we don't know enough about Cayley graphs.
What is minimal Cayley graph?
So Cayley graph,
I know Cayley graph.
I get from, yeah, but maybe not everybody knows, right? So maybe Cayley graph I get from a group and a set of generators, or conjecture, because otherwise everybody will be confused. And I basically have a vertex for every group element, and then I have a connection between two of these if I can get there via one of the generators. And if the set of generators is inclusion-wise minimal, then it's a minimal Cayley graph. So this is a group, this is a set of generators.
Okay, I guess you need minimal for the implication to hold as well, because you can.
So you're coloring edges by the group element, which is a generator element, right?
This is the
Generator
idea,
is
exactly.
this.
So if I use the minimal generator set as my coloring, then I will have basically coming into a vertex and going out of the vertex with one generator. So this gives me a coloring that fulfills this weird two adjacent thingies condition. So this is where this comes from. And it is a problem that has also been studied by a lot of people, but I'm also gonna mention one further conjecture that was made last year by Marco and Knauer. Kolja Knauer being, by the way, the person who got us into thinking about all this stuff. And they conjectured that actually graphs admitting a proper node-only edge coloring have bounded chromatic number. So I make a stronger conjecture than this. No, it's not actually stronger, because this is it's a smaller graph class, right? Graphs admitting proper node only edge coloring. Have bounded chromatic number. Right, so then we only look at those graphs that admit even a proper no only edge coloring, and try to prove for them first that they have bounded chromatic number. So they said, okay, if we cannot prove that, maybe we can prove that. And the result I'm presenting today, oh my god, it's right over there, so you can see all of it. The result I'm presenting today disproves both of these. For given natural numbers G and K, we construct a graph so that has large girth, large chromatic number, and a proper no lonely edge coloring.
Is girth thing important?
No, the girth is kind of just in the end we also got girth, right? So if you look at the conjecture, we really didn't set out to also get high girth, but as the construction also gives high girth, it's kind of nice to include it into in the result. But you notice that if we prove this, so we find this family of graphs and they have large chromatic number, but they all allow proper node on the edge coloring, then this disproves both of these, the weaker one and the stronger one. So it turns out these are both false. This shouldn't come as a surprise to Babai though, because in '95 he went and said, oh, forget everything I said, I conjecture the opposite. And actually said, oh, I think actually node only color graphs have unbounded chromatic number. That's a different conjecture by Babai. So in a sense, we proved and disproved the conjecture by Babai at the same time. Very convenient.
Disproving 1978 is more impressive.
Yeah,
from
so
90s.
Quite a bit later, he over 20 years later, he changed his mind about this. This kind of constructions of graphs with large girth and unbounded girth, unbounded chromatic number, these have been around for a while.
Sorry, can I ask, if a graph is a Cayley graph but is not minimal, can we prove that this graph is not only graph?
Cayley graphs in general have unbounded chromatic number, and yes, have unbounded chromatic number. In any case, whether they have a node-only color or not.
So we don't know whether
This is not a conjecture on normal Cayley graphs.
What's the bound for the minimal largest Cayley or largest chromatic number of a minimal Cayley graph? Do you know?
It's 5. No, it's 4. So we know for 4 that they exist.
So the
This is
conjecture
quite recent result by these guys. I will draw it. I will draw one of them. But we do not know them to have unbounded chromatic number. Obviously, otherwise we would have
Right.
already an answer to this. But the bound is actually surprisingly small.
Yeah.
So it's open whether there's a minimal Cayley graph of chromatic number 5 or larger. Well, the last time I checked, it was open, maybe because it's a kind of hot topic. maybe somebody's found one by now. But last time I checked, this was like this construction of a Cayley graph of chromatic number 4 was the best that we had. I can draw it. This looks like this. It's 7, yes. It's important, this is not the only example, this is just the one that I can easily draw, the others are a little bit more complicated. So they find more examples of chromatic number 4.
What kind of group is it?
I will give the group in a moment.
Uh-huh.
So the group is Z3 and then this weird semi-product Z7, right? So
There's
after-
something wrong with the one on the right.
Oh, yes. Oh, yeah, you're right. This should, of course, go all the way. Sorry.
Yeah, and then the one to the right is wrong somewhere
Oh,
else.
the last bucket?
The last, this is like a circle with a little, there's something.
Yes, yes, yes. Sorry, if
Something missing.
you
It doesn't
stand
matter
too
too
near
much.
to the board, then you easy overlook this.
Yeah, for sure.
Sorry, the one and last one?
So I got this.
It's supposed to form a cycle.
Yes, this. Oh, I'm just missing an edge. Oh, it's good.
Good. Yes, yes.
Okay.
Yes, I just
Just missing an
forgot
edge.
the last edge. Okay. So this is the
It looks.
first generators 0, 1 and 1, 0. And the chromatic number of this graph is 4. I'm not going to draw this. If you are bored, check. Yeah, and this is one of a few examples that they found. And these have chromatic number 4. And it's also kind of weird that it works for these. Like, I thought, okay, maybe it's like a prime thing, right? But like for 3 and 5, I tried that has chromatic number 3. It just doesn't quite do it. And if you do 9, I think it also doesn't work anymore. It's just this weird combination. I didn't quite understand where this comes from. So chromatic number on minimal Cayley graphs, kind of a complicated thing. So the conjecture still remains open for whether we can do it for minimal Cayley graphs. But for today, we do the node-only color graphs, and for node-only color graphs, we know that we can construct this. Yeah, and these kind of constructions, like I said, they come a long way. They have been around for a while. So graphs of large girth and high chromatic number. So I think Erdős in 1959 gave a proof via the probabilistic method that these do exist, right? And then we have the first constructive one by Lovas, 1968. So this is probabilistic method. And this is the first constructive one. And since then there have been a lot of constructions with a lot of different properties people use for all kinds of different problems. And our construction for this graph class also gonna be explicit. And it's based on something that is called Tutt's construction. This will fall if I don't. Okay. construction that most of you might also know, but I'm gonna quickly sketch it because our construction really works the same as based on this. So we want to understand how it works. So Ted's construction constructs graphs that are triangle free and of unbounded chromatic number. We start with G1 being just a single vertex. It's triangle free and has chromatic number 1. Then let's define n to be the size of the graph GK. So the graph we constructed in the step last, and let's construct GK plus 1 from it. For this we start with a large independent set, and it's of size k times n minus 1 plus 1. No edges in this. And now for every subset of exactly n vertices, I add a copy of GK, and because I have exactly n vertices in the subset and exactly n vertices in the copy of GK, I can match them. So I add a matching between these. And this I do for every subset.
Subset of certain size or any
Of size n.
size n.
Of the
Okay.
size that my last copy was.
I thought it's you.
Let's put this. What, you?
No.
Sorry, yes. This is why I never call anything u if I have an n around, because then nobody can read it anymore. So for every subset of size n, we add a copy of GK and match these.
So it's an arbitrary projection for matching?
Arbitrary, yes. I don't really care, just any way. And now I claim that GK is not k minus 1 colorable.
GK plus 1? GK or GK plus 1?
GK is not k. So if I construct all these things, right? You can also say GT is not t minus 1 colorable if you want to get away from the construction, right?
Yeah.
But I construct the graphs like this, and then it gets larger and larger, and in the end I say in every step the chromatic number grows by 1. So I cannot color the step t with t minus 1 colors. And why is this the case? Assume I could, right? Then I have, because I have k times n minus 1 plus 1 subsets, and here I have a monochromatic set of size n. So I find one of these sets, and they're all colored the same color. And now this color, because I'm matched to every single vertex, so every single vertex in here sees this color, I cannot use in this. So if I'm coloring with colorable with k minus 1 colors, though, that means that I found a coloring for the step before, gt minus 1, with even less colors. So t minus 2, which is a contradiction. And also because I have this matching here, and the thingies are triangle free, I also don't create triangles, so I stay triangle free with every step. Questions? Because we're gonna do a more complicated version of this in a minute, so.
Sorry, can you do this again then? I don't follow the inductive part. The map, the colorability.
The colorability. Okay. So because of our set size of the independent set, if I now color this, so let's say we look at the stat k plus 1. And now I say I color it with k colors. Then I find a subset by pigeonhole principle that of size n that has one of these k colors, monochromatic. Right? Let's say it's like
Okay, got it.
this set of size n, it's monochromatic. For the set, there is a copy which is matched, so this monochromatic, this color is not used in here, so I can color this with one less, even, and then I get a contradiction to the induction hypothesis. Okay, so far so good. Test construction. So for the remainder of the talk, we have 3 steps to do. First, I introduce something that I call tranquility. It's a property of hypergraphs. Then we will construct tranquil hypergraphs with large girth and large chromatic number. These then GKR, because this hypergraph is going to be R uniform. So uniform hypergraphs with large girth and high chromatic number that have this extra new property, tranquility, that I will define in a moment. And then we're going to do the tensor construction just with hypergraphs.
What is the girth of a hypergraph?
It's the same. It's the length of a shortest cycle.
What kind of cycle? Like you may have several ways to define a cycle.
Yeah, it's the simplest form of it. I think it's called a Birch cycle. You just say that you find a cyclic connection of edges. Whether these touch somewhere else, you don't really care.
You mean V1, E2, V2?
You find a sequence, cyclic sequence of vertices, each following 2 are connected by an edge. No further restrictions on this. Also, the hypertensor construction isn't really constructing a hypergraph, it just uses the hypergraph for the construction. So it's also not entirely so important how this girth condition looks. Okay, so what is a tranquil hypergraph? I will write the vertices in. I'm going to define this by example. It's a very small example, but who has ever worked with hypergraphs knows that they become very undrawable very quickly, so we're going to stick to a very small example. So I have a uniform hypergraph. Works for every uniformity. Our uniformity is 3. Very easy. And now I add a labeling to my hypergraph such that for every edge f, I map the vertices in it to 1 to R. What does this mean? For every edge I have 3 vertices in it, and I number them 1 to 3.
So in a sense, you are giving ordering of the vertices inside an edge.
Yeah, basically every edge orders its vertices, so vertices can get a lot of labels depending on how many edges they lie in, or A goes without any labels because it doesn't lie in any edge. But every edge now has a vertex labeled for every value of my uniformity. And now if I look at a walk, at a closed walk in my graph, right? So a sequence of vertices and edges between them, such that consequent vertices lie in the same edge. Closed walk. Then this gives me a multigraph, and I call this multigraph pH, lambda, and W, because it depends on the hypergraph I come from. So the hypergraph I come from is H, this is H. The labeling that I chose for all the edges, and the walk. And this graph has the vertex set 1, 2, R, so 1, 2, 3 in our case. And I add for every hyper edge in my walk an edge between two vertices here if it connects along my walk the two labels. So because the brown edge connects the vertices C and D and they are labeled 2 and 3, it gives me an edge between the two vertices 2 and 3. And the green edge connects 1 and 3, so I get an edge between 1 and 3. And the orange edge connects 1 and 2, so I get an edge between 1 and 2. And however I started with my walk and my labeling, I will get such a graph.
You allow loops, right? If you start from 2.
I cannot do a loop because I have every label exactly once.
No.
In the multigraph.
It is a multigraph, yes, but a loop I still can't get because which edge is supposed to give me a loop?
C was labeled 2 by the green thing.
Then I would just get a second edge from 1 to 2.
Then I don't understand the construction.
Right? An edge always connects two vertices in my walk. It also doesn't matter.
I see. Okay,
It doesn't have loops, but it also doesn't matter
Right,
whether
right,
it has
right.
loops. Not important. Important is that if I find a labeling such that for every walk this graph is bridgeless, then my graph is tranquil. So if there exists a lambda such that all P, H, lambda, W are bridgeless, then my graph is tranquil. So now I need to get those graphs somewhere, right? So as you can guess, the property is very specific. The property we understood first. From the construction we wanted to make, we understood we need this property. Now the hard part was, okay, find a hypergraph with that property. Why would it even exist, right? But we were lucky, somebody else proved that it exists. And this is a result by Vogt. somehow a combination of two of their papers, also already quite a bit ago. And they construct a graph, or actually they didn't construct, they just proved stuff about it. So there is a graph you can get by something called the van der Waerden construction. And the van der Waerden theorem is then that I get that these graphs have unbounded chromatic number. And I get it as follows. From for every vertex, for every point in Z to the D, I draw 2 because everything else would be a chaos. For every point in Z to the D, I add an edge between any vertex that's exactly R apart in each of the directions. So if I had a third one, I would do R in this direction, and then I add an edge containing all of these things. All of these vertices that are plus R in one of the dimensions. And I add these for all R. So my edges kind of look like this. So right now these are actual edges, but as soon as I have more than 2 dimensions, I have that these are hyper edges of exactly size D. D is the dimension. So this is a D uniform hypergraph. And it has these have unbounded chromatic number by van der Waerden's theorem.
Oh.
And
D uniform.
D uniform infinite hypergraph actually. Right?
So are you selecting the vectors of the same distance, or?
Yes.
But then when you increase the R, then you have a different.
Then I still have one member for each dimension though. So the edges are all the same size.
Oh, I see. So the.
I add all of them that are 1 away, 2 away, 3 away, 4 away.
So
Each separate edge.
okay.
Right?
Oh, so the hypergraph is for each R you have a hypergraph, or
No, the hypergraph is I add an edge to my hypergraph for all of the distances, but 1 edge per distance. So the edges are all of the same size because the dimension doesn't change. Right? I get a graph CD for the fixed dimension. And I add these edges for every point. Right? So they also intersect. If I now look at this point, I get like this edge and this edge, for example, right?
Nah, what I'm not sure is if you are at the origin,
Yeah.
then do you add 1 0 0? I mean, you have a 1 0 0 0 and 0 1 1 1 in distance 1, right?
No, I have 1 1 1 1 1 and I have 2 2 2 2 2 and I have 3 3 3 3 3.
Huh? So, and what I'm
I see. So I have 1 0 0 1 0 1 0
Yeah,
and
yeah.
0 0 1,
right.
and I have 2 0 0 0 2 0 and 0 0 2,
I see.
and I have 3 0 0 and
So
0 3 0
you don't
and so
add
on.
you don't add like 1 1 0 or this kind of.
No. I only ever have 1 entry per dimension.
So you just take
But I have
direction.
1
I see.
entry for
I see.
each dimension, and
Uh-huh.
that's why my hypergraph is D uniform.
Okay. Now, I
Okay.
initially thought that you're adding all the but this is the same distance, but
Yes.
no.
So, Prömel and Vogt, they proved that I can actually find a finite induced subgraph of this that has still a large chromatic number and also high girth, because actually this thing really has low girth, right? So, finite induced subgraph of chromatic number large. Okay. And also large girth. And this I want to call my graphs H, G, K, R. As the subgraph would still are uniform, or D, maybe D uniform. Now it's finite. It has large chromatic number still, and large girth. And what we also proved is that this thing CD is also tranquil. And if I take an induced subgraph of a tranquil hypergraph, of course I stay tranquil. Right? Removing stuff will never suddenly make my graph non-tranquil. I can just keep the same labeling. So this gives us now these hypergraphs that I wanted to have, that have large girth, large chromatic number, and are uniform and tranquil. So I have this insanely weird property of allowing this labeling of all the vertices by the edges, such that I get this auxiliary graphs being bridgeless. So now comes the hypertouch construction. Now we use our hypergraphs that we have. Large girth, large chromatic number are uniform. And from this, construct our graphs large girth, large chromatic number. The girth just comes from this, so we fix a G. I will just stay large girth. The chromatic number is the one, so the K is what we do induction over. And we start, as for touch construction, with a single vertex. Everything fine so far. And now for constructing GK, we use the graph H G over 3, K and R. And R here is the size of the graph we just constructed. So like before, the TUT construction used the n, the size of the graph we just constructed. In this case, we call it R because this will be the uniformity of the hypergraph we use as the base for the step. And because this, let's call it H so I don't have to write all of this over and over again. So because H is tranquil, we get this labeling from each F to the set 1 to R. Right, because it's tranquil, I get this labeling for every of the edges. For every edge I get an ordering of all the vertices that lie in it, and then it has this weird property of building auxiliary graphs that are bridgeless. So now if I look at such a graph, such an auxiliary graph, then this thing is bridgeless for all W, which were closed box. now we come to the construction. So we again make a large independent set, and this time the independent set is the vertex set of H. Right, so I don't actually add the hypergraph, but I add the vertex set and remember that there were edges in my hypergraph on these vertices. Right? And now, in Tad's construction, we just went and took every subset of size n or r, and now we don't just take any subset, we take the edges. Right? So there used to be an edge here of size r. Now I add for this its private copy of gk minus 1. But now I have this labeling here somehow, right? And I use this labeling to decide which vertex to match to which vertex here, right? So if I order all the vertices in this graph, so I fix an ordering of all the vertices in this graph, so I fix an ordering on the vertex set gk minus 1. And this I use all over my construction to check. So if this is now v1, I match it to the vertex that is labeled 1 in this hyperedge by this labeling lambda. So I basically use lambda here to decide which vertex to match to what. So this v2, v3, vr, and so on. And this I repeat for all the different edges. They get their own copy. And I match them according to what the labeling says. So now, why does this construction have all the properties that we want? Meaning it has high girth, high chromatic number, and a proper no-lonely edge coupling. This we want to prove. High girth it has because our hypergraph has large girth, right? So if I look at a cycle in my graph, because this is an independent set, it has to walk through one of my copies, and then it has to walk through another of the copies, and so on. And in the end, after it has done this a while, right, it has to come back to this vertex. This is how a cycle looks. So the cycle, because I can only walk through a copy to get somewhere within the same edge, there has to be an edge connecting these two things between leaving and coming back. Leaving and coming back, leaving and coming back, leaving and coming back. So these are all edges, and they form a cycle in H, and if H is of large girth, then so has to be this graph. And this is why we used G over 3, because in the end, because I have to go a step and come back, because it's a matching, I cannot just come back immediately. I have that this cycle in my graph is by a factor 3 larger than the one that I got in H. So the girth of this graph is G. Why does it have large chromatic number? This argument works also exactly like it did for Tad's construction. If I wouldn't have that this has a chromatic number k, then I find one of my edges that is monochromatic, because my hypergraph is not k minus 1 colorable, right? But that's fine because this is not an edge, this is an independent set. I would totally be allowed to make one of those edges monochromatic. But now that it's monochromatic and I have this matching to the copy, I do not have enough edges to also, colors to also color this. So I get a contradiction to the induction hypothesis. So it actually has, again, large chromatic number. The complicated thing to prove is that it actually has a no lonely color, edge coloring, right? And then how do we get this? So we color all the copies by the coloring we get from the induction hypothesis, and now we add a new color for each of the matches. I don't really care of how many colors I use, so I just introduce a new one for each of these matchings. It's very easy to see that the new colors are completely fine, right? They are in a matching. If I want to close it to a cycle, I have to walk through the matching twice. So each cycle using one of the matching edges will use another of the same edge matching and will have therefore a different color also, a different edge also of the same color.
So for every matching for every subset of Y, you choose same color, right?
Yes,
One
exactly. So basically I add number of edges in each new colors, right? While all the copies I color by the coloring I have from the step before, and all the same. And this is important now that I colored them all the same, because I also took care in matching them to my edges to match them to the right labels, right? This is now important, because now if I look at a cycle, and now assume I have some color here and it's lonely, or I take this color and I want to prove it's not lonely, then this color lies between two vertices, Vi and Vj. Right, so I have, but actually it lies somewhere along a path between Vi and Vj. It doesn't actually have to be this edge, right? The cycle somewhere enters my my copy, and this path can of course be longer and then goes back. And this are the indices I and j. So I walk on a path Q between Vi and Vj, and somewhere I use this color. Now so I have this edge ij in my auxiliary graph for the closed walk I get that the cycle gives me, and because this is not a bridge, there is somewhere a different path between I and j along this walk, right, that also closes this. To be a little bit simplifying, let's just assume there's a different edge and I also go from Vi to Vj via path P. This of course doesn't have to be in a single edge. It can be that this happens over several other copies. But for the sake of presentation, let's assume the easier case. And I actually get a different edge, a different copy where I also walk from I to j, which then would, in my auxiliary graph, look like I get a parallel edge. Right? But of course this path here could be longer, and then I actually have to walk through a few more. But let's assume that. So that means I have somewhere here my path Q that lives in this copy, and I have a path P that lives in the other copy. If they are disjoint, I just take them from two different copies, but they live in the same graph, so I can also just draw them into the same graph. Right? And the coloring is the same. So I draw them into the same graph. If they are disjoint, they build a cycle. So somewhere here has to be a different edge that also has this color. Right? If they're not disjoint, then they still contain somewhere a cycle that contains this edge. And on the cycle, I have to have a second edge with this color, because the edge coloring that I chose for my copies, that was a proper edge coloring. Proper no lonely color edge coloring. And because I color these matchings always, this is why I attain to actually be a proper coloring, because I never create in this two edges of the same color incident to one vertex. And this finishes the construction. So we have this class of graphs of unbounded chromatic number, large girth, and with proper edge colorings that are lonely colored. And that also finishes my talk.
Thank you. Any questions?
Yeah.
Is there any relationship between chromatic number and the smallest number of colors we did for the proper non-lonely edge coloring?
Not that I know of. We created a lot of colors, right? Like way more than the chromatic number. So we never consider for this kind of non-lonely edge coloring. We never cared about the number of the colors. So I'm not aware. I would be surprised if there was an actual connection.
Okay.
How symmetric is your constructed graph? Can you say like it's transitive or blah blah blah? Some of the properties, whether like slightly larger class of Cayley graphs still have counterexample.
We really tried to make this a Cayley graph construction, and we really didn't get how to do this with the matchings, right? Like this is really weird because this is an independent set. So somehow generators would always like move you into one of the copies, but then why would you first, to get to any of the other elements here, first have to move back to the independent set? It was totally unclear to us how to force this with Cayley graphs. But like I said, we're like really not the experts in Cayley graphs, so maybe there is a trick. But to us, this touch construction didn't seem very compatible with Cayley graphs.
If I contract those matching edges and just think of the conjecture in terms of parallel.
If you contract the matching edges, you basically get the copies being drawn into the
Same thing,
into
right?
the thing, right? So they then overlap a lot.
Yeah.
So you first of all very definitely get a multigraph, right?
Right.
Which you might be fine with, I don't know, but
But the same argument of increasing chromatic number doesn't work, right?
no, the chromatic number argument fails then.
Right. I see.
Yeah, but also the girth argument gets somehow, because now you suddenly can. Yeah, I don't see how that would work. You cannot just contract it.
So again, I don't completely know what was Babai's intuition for. I mean, you tried to explain using Cayley graph, but for example, I can also look at lonely coloring as sort of almost proper edge coloring, such that no cycle has a unique color.
Yes.
Right?
Yeah.
But then this can probably be tweaked beyond this. Like the first condition can be tweaked to say that every vertex is incident on some constant number of edges, and you can choose that constant, right? So if I allowed you to relax this first condition to let's say having a vertex with at most 3 edges of the same color or 4 or 5, do you think that in those scenarios having such proper such lonely colorings would imply bounded chromatic number? I mean,
It's already not bounded if you only look at proper colorings. And this graph class will always be contained, even if you allow more, right? Because I actually only need proper. You just make the graph class larger, but it already has unbounded chromatic number.
so yeah.
So when he revisited the problem after 20 years, did he give any reason for why he then thought that it was false?
I don't actually know.
Don't know. I just thought maybe this isn't the right way to put it.
Because he also didn't give a proof, right? So I don't know what actually caused this change of mind. Maybe just he tried proving it for 20 years and failed, so he decided maybe it's wrong. No, I don't know.
Could be.
Right. Any? Yeah.
What is the complexity of deciding the resistance of such coloring? Is
So
it
only coloring?
That's a good question. I do not know.
Is it in NP? Is it in NP?
Yeah, you can always give
Yeah, yeah.
coloring and check whether it has the condition right.
Is it easy to check?
Number of colors is bounded anyway, so.
To go through all cycles and check at least the triple way, right?
Yeah.
Oh.
Actually, yeah, you have to
The
go
number of
through
cycles,
the
number
number
of
of
cycles,
cycles.
number of
There's
cycles
actually
matters.
a lot of cycles. Yeah, maybe. Yeah, I don't know.
You need to check that for every edge. If you look at in the complement, like you need to check for each edge that the complement does not connect. Like basically.
Ah,
should
I see. Wait.
What?
Essentially, finding that having an edge with a lonely color means that
Yeah.
if you look at the complement of that color class, as in the graph, all the color classes minus that
I
one,
see.
Yeah.
it connects the two endpoints.
These two. I see.
Right,
So
right.
The
Makes
complement
sense.
can be connected. It can
Yeah.
just not contain the
Yeah.
two
Yeah,
endpoints.
so
Yes,
then
yes.
you can check.
Yes,
Yes,
and
you
that
can
you
check.
should be able to check. Yeah. Good.
At least it's MP.
But that's a satisfying answer. I'm not so sure. Yeah, maybe there's more efficient versions. I don't know. We didn't actually consider it algorithmically.
So, but what's the complexity of the normal chromatic number, like the vertex chromatic number on claw-free graphs or line graphs?
On what free graphs?
Claw-free graphs or just line graphs?
Of chromatic number.
Line graphs. That's edge kind of number, so
Yeah,
getting
that's why I-
exactly is NPR.
But it's
Okay.
always
Yeah, but
delta.
within one error should be easy, right?
Yeah, more precisely than that, I also don't know. No.
Right. Any more questions? So if not, let's thank the speaker.